All right. So today we will actually continue the topic we started before the test, and that was the topic of root finding. So we mentioned so far two methods. One was bisection. Basically, find the interval, and that interval we will call the bracket if on one end of the interval we have a function that is positive, and the other end of the interval we have negative, or the other way around. Either way, functions should have opposite signs at the ends of that interval. And then you literally just keep splitting that interval in half and choosing the better half. And the better half is the one that has the same bracket functionality. So basically, if I had here 12, 16, and this is my function, okay? So it's positive here, negative here. Then I divide it in half, and between two options, 12, 14, and 14, 16, I'm going to pick 14, 16 because I, again, have f of 14 times f of 16 is less than 0. And that's my choice of bracket. And I keep going. When do I stop? I'm going to pick an orange shirt today. When do I stop? You never get to exact point. Rarely you get exact point, but you get close. How do we define close? So length of this interval has to be small enough, and I decide what's small enough. So this is one of the first lessons we have in any software. Software works on problems numerically. Rarely the solutions you're looking at are exact. Therefore, software made a choice for you how close it got to the solution. So that's something that is built in, and often the software doesn't tell you. So when you use software as black box, you will typically have a number of options there that have been selected by somebody designing it. Okay? Hopefully it was selected well, so it's actually still going to be good, but it's something to have in mind if the software fails to give you a solution that makes sense. All right. So this was our bisection method, and actually I have it here. This is what we worked on in class. This is one way to solve it. So basically I picked my bracket. This is just a script. And I say, okay, while this difference, which is basically how close I am to my root, is larger than some fixed number that you pick, some tolerance, then find the midpoint, okay? And I actually, especially, I had a side function called parachute that actually computes precisely this for every input value of x. So I basically compute these three values, and then I check if f of xl, so that's my lower bracket point, and this midpoint is less than 0, that's my interval, so my new upper point becomes xr. Otherwise, if f of xu times f of xr is less than 0, then my lower point becomes xr, and I keep going. This is the ideal case for a while loop, okay? Because I want to stop when I'm close enough, and I never know 20 steps ahead how close I will necessarily be. Okay, cool. And then I can just print it at the end. So this was our bisection method. And then I mentioned last time that we have another version of the method that simply is trying to improve on the choice of this midpoint. So midpoint is a crude way. It's like I don't even look at the function f. I simply split the interval in half and keep going. That can sometimes be very slow. So there's an idea. Whether that idea works or not, we don't know right now. And actually, in general, it should work, but there will be cases where it won't work. Okay. So basically, there's idea is like, okay, instead of splitting in half, okay, this interval, I split it in half and go with this point. Let me actually see. So this is actually the point that I'm looking for is this one. And I don't know where this is because that's what I'm looking for, but I can approximate my function f with this linear version, okay? And I'm just going to look for the intersection of that approximation to function f and my zero line. And that's gonna be my next choice. And again, I will do the same thing. I will check which bracket works better and keep going, okay? So this is a geometric consideration to actually find where this XR is, and by this triangle and this triangle being similar, okay, so these are two similar triangles, essentially you will find that f of xl, which is this line here, actually negative this line in this case, divided by xr minus xl, so this divided by this should be the same as this divided by negative this in this case, because I already multiplied by -1, and this gives you this relationship. And from it I can simply solve for what xr should be. Xr is xu minus f of xu times xl minus xu divided by f of xl minus f of xu. So you can actually recognize the slope. This is the slope of that line over there. All right. So in general, when this works well, I'm going to find out that my error, and error is how far I am from my true solution, okay, goes down much faster with false position, so that results in a faster method. And bisection goes something like this. In general, not always. Unfortunately, in root finding, I really very much depend on my function. So let's check it for parachute. So take that bisection, okay, dot m. If you don't have yours, I have uploaded the MATLAB file that I just posted, that I just showed you right now. So if you want to work with that, and modify it. Okay. So basically, save it as a false position dot m, and basically change that line that computes my XR, change it to this new one, and let's see how fast it works. Now, in order to compare them, you will also have to compute relative error. Okay? So I will actually have to compute relative. You can, again, you can either work with bisection, that is yours, your file, or this one. Oh, I probably didn't upload parachute.m. Let me upload that. So whatever works for you, work with my code or yours. So I uploaded both parachute.m and bisection.m. So key change is this. How do I pick my next XR? So you will have to change that based. And second thing, I want to figure out how fast they are. So I actually have to look at the relative error at each point. So you have to modify this script a little to find the relative error. Yes, I can. Here we go.